So let me summarize what we did. I like always to start the lecture by summarizing what we did. So basically, we were talking about shortcuts. So we have the series circuit, and we have the parallel, and we are almost done with this. So we said that when we have resistors in series, R1, R2, R3, R4, etc., and we identify being series when they share one node. So R1 and R2 share one node, and nothing else share this node. R2 and R3 share this node, and nothing else share the same node. Now, we say that since R1 and R2 in series, R2 and R3 in series, then all of them in series, indeed up to R4. And we said when we have this configuration, we said that R equivalent is equal to R1 plus R2 plus R3 plus R4. And we said that we can substitute these four resistors but by just one resistance. Then we said if we have a voltage source here, Vs, and let's say if I want to have the voltage at R2, I will call it V2, then we said that V2 is equal to Vs, the main supply, times R2, which is the resistance of interest, R2, divided by the summation of all resistors, R1 plus R2 plus R3 plus R4. Now, for this to happen, the voltage source has to be also in series with all the resistors, and we said that this is voltage division, another shortcut. Now, for the parallel, when we have R1, R2, R3 in parallel, we said that the 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. And also we said if we have only two resistors, R1 and R2 only, then 1 over R equivalent is equal to 1 over R1 plus 1 over R2, which is equal to R1, R2, R1 plus R2. So your R equivalent is nothing but the multiplication of the two resistors divided by their summation. So this is what we did. Now, there is another shortcut called current division. And from its name, here is voltage division. So the voltage source has to be in series with the resistors. Here, current division. So it's a current source, IS, in parallel with the resistors in parallel. So if this is the case, and if I want to find a specific current in one of the resistors, how I can find this in one shortcut. So this is the first thing we will be covering. So we have here I total, we have R1 and R2, okay? And we have a current total, and I want to find, let's say, I1 or I2. So let's derive this. So I can find the R equivalent here, R equivalent, these two are in parallel. So they are equal to R1, R2 over R1 plus R2. So this is an R equivalent. So I can change this basically to a current source, which is I total, with an R equivalent here. Now, this voltage V across R1 and across R2, it's the same voltage across R equivalent. So this is exactly the same voltage because they are all in parallel. So their equivalent resistance they will maintain the same voltage. So here your V is equal to the current I total times R1, R2 divided by R1 plus R2. So this voltage across R1 and this voltage across R2 is the same. Why the same? Because we agreed now, when we have components in parallel, they will have the same voltage. If the components in series, they will have the same current. Okay, so if I want to have I1, what is I1? Using again Ohm's law, I1 nothing but this voltage V divided by R1. So if I substitute here this formula, it will be exactly the same thing, but I will just take out R1 because I am dividing by R1. So this will becomes equal to R2 over R1 plus R2 I total. How about I2? I2 same thing, V over, but now over R2. So this becomes, now if I divide this by R2, this will be out. So it becomes R1 over R1 plus R2I total. So let's try to generalize this. So the current in the resistance R1 is equal to the main current times the other resistance R2 divided by R1 plus R2, the summation of the two resistors. I2, the current in R2, is the main current times the other resistance divided by R1 plus R2. So this is a bit different than the voltage division, where you multiply the voltage by the same resistance of interest. Okay, so this is the difference between voltage division and current division. The question is, what if we have more than two resistors? Here we have three resistors, and I am interested in this current. Okay, so how I can find this current? The voltage division says that if you, as I mentioned, if we have 4, 5, 6 resistors, it doesn't matter. You multiply the voltage by this resistance divided by the summation of all resistors. What if I have more than two resistors? Because the formula that we derived here is just for two resistors. Then I have to change this, reduce this in a better way. So to the resistance that I am interested to find the current, and then I will have an equivalent resistance for the rest of the parallel resistors. So this means that this 15 amp stays as it is. This 10 ohm stays as it is. And here is my current I am interested in, which is your I1. Okay. And then I will have here my R equivalent, which is these two resistors that they are in parallel. I will be substituted by one. Then now we will go back to the previous case when you have only two resistors. So in parallel, you have to reduce the circuit to two resistors only. Now, what is R equivalent? You can, these are two resistors in parallel. So we will basically multiply their values, 30 times 60 divided by 30 plus 60, and this is equal to 20 ohm. So this becomes equal to 20 ohm. Now, since I have two resistors in parallel, now I can find I1. So to find I1, it is the main current, 15 amp, times the other resistor, not the 10 ohm, the other one, which is the R equivalent, which is the 20, divided by the summation of the two, 10 plus 20. So this is 15 times 20 divided by 30. Okay, so this is 1, this is 2, so this gives me 10 amp. Okay, what if I want to find the current that goes in R3? What should I do? What do you think, guys? If I want to find I3, not I1, what should I do? Okay, excellent. Excellent, Mariam. So what you need to do first, you need to find the equivalent of R1 and R2. They are not, you don't add them. Okay, they are in parallel still. So it is, you find R equivalent, so your circuit basically will become equal to this. 15 amp will find your R equivalent, and then you will have here R3. This is your I3. So your R equivalent is 10 times 30 divided by 10 plus 30. And you can do the same thing. Let me have a comprehensive question that has, you need to do both voltage division and current division. Okay, so in this question, as you can see here, you says here, find Vx using voltage division, then find Is, and then use it to find I3 using current division. So we'll see how we can do this. So first of all, these two resistors, they are in parallel. Okay, so I will reduce this circuit to the following circuit. Plus, minus. This is 100 volt. Nothing happened to it. R1 60 ohm. Nothing happened to it. Now these two, I will put the R in parallel. So I will find their equivalent, 30 and 60. It's similar to the, so this, we know this is already 20 ohm. Now, from this, I need to find Vx. We said that the Vx is the voltage of these two parallel resistors, and it's the voltage across the equivalent. Now, this is a typical voltage division. I could not apply voltage division here, and I want to insist here, and because this is a common mistake. R1 and R2 is not in series. They share one node, but R3 share the same node also. R1 and R3 also, they are not in series. Okay, but R1 is in series with the combination of R2 and R3. When I combine R2 and R3 to one resistance, which is the 20 ohm, then it is in series with the 60 ohm. Now, once everything in series, the voltage source, the two resistors, then I can find Vx easily, which is the 100 volt times the same resistance that I'm interested in, divided by their summation, 20 plus 60. Okay, so this is 100 times 20 divided by 80, cancel, 4. So this is 25 volt. So here we will have a 25 volt. Excellent. Also, it says here, find Is. Is this current that comes out of the source. So this is your Is, which is the same current here. Is here is the same as this current there. And if you apply KVL, or if you find the equivalent resistance, which is these two are in series, so this becomes 80, this is 100 volt. So your Is is equal to 100 divided by the 60 plus 20. It is 100 divided by 80, which is equal to 1.25 amps. So we found this current, Is, which is this current. Now I want to find I3 using current division. Now I am working with this circuit, but this circuit is equivalent to that circuit. I cannot find I3 from this circuit. Why? Because I already combined R2 and R3 in one resistance, which is 20 ohm. So I cannot here find I3. But if I go back here, because these two circuits are equivalent, and now I3 here is 1.25. So I have a current here entering these two branches in parallel. So now current division can be applied. And your I3 is equal to the main current, which is the 1.25, times the other resistance, which is the 30, divided by the summation of the two, 30 plus 60, and this is equal to 0.417 amp. So this is your I. So you can see here, this question is a combination of different things. We have parallel resistors, we add them, we reduce it to this circuit. Then we have Vx using voltage division, because Vx is the same as this. Once we know Vx, then we can find also Is, because here we have 100 ohm and these two are in series. So we have the parallel, we have the series, we have the voltage division, and then once we know Is, we have the current division. So everything we learned so far, we apply to this circuit. Parallel, voltage division, series, and current division. Okay, if you understand this example, then you should understand everything. Can you go back a second? You explain how we get I3. No problem. Let's go back here. These two circuits are equivalent to each other, meaning that the current that comes out of the supply is the same current. Okay, so the current Is that I found here. Now, remember, this Is is nothing but 100 volt, this 100 volt, divided by the summation of the 60 plus the 20. Okay, in other words, my circuit now is reduced to this 100 volt, and here my 80 ohm. Now, this is your Is. Now, your Is now becomes very straightforward. The voltage divided by 80. So I hope this is everyone understand this. Okay, so this Is is the voltage that comes out of the 100 volt, which is here. Now, this is the same as this Is. These two currents are exactly the same. So we have a current that enter here equal to 1.25. Okay, so I have here 1.25 amps entering here. It will see two parallel paths. So we can apply current division. So your I3, okay, is equal to I3 is equal to the main current, the 1.25, times the other resistance. Remember, parallel, you have to have two resistors in parallel. Okay, so the main current times 30 divided by 30 plus 60, and you will get the 0.417 amp. Okay, hopefully this explains. Let me see here if there is any other concerns about this. Okay, uh, Da Young Ju is asking why this is the current times the other resistance. This is what we just derived here in the previous slides. Maybe you came a bit late. This is what we derived here. If you go back here, this is what we derived in the current division. In the current division, you can see here that I1 in R1 is the total current times the other resistance divided by the summation. And here's the derivation for that. So for the current division, it's always the other resistance. For the voltage division, it's the same resistance. So this is the difference between voltage division and current division. Before I move forward, I want to make sure that yes, it's always the other resistance. Yes. Okay. Now let's move on. So what is left here in this slides? We have two important application circuits. These two circuits are used in many applications, especially the second. We will use both of them, by the way, in the lab. The first one is called a potentiometer. In your kit, you will have it. This is the potentiometer. Okay. Okay. So basically, there is a knob that rotates, and there are three terminals, as you can see here. There are three terminals, 1, 2, and 3 terminals, and this is something that you can rotate around. Okay. Called potentiometer. So what is this? Is basically this is how it look like inside. So there's something that sliding wiper that goes here. These are the three terminals. Okay. Two fixed ends and one variable end. So if this is 1, 2, and 3, this is 1, 2, and 3. So this, what I'm rotating here, when I rotate here, I'm moving Number 2, up and down, up and down. Okay. Now, the V out is the voltage between this point and the ground. And this is the Vn. So basically, this circuit is nothing but something like this. Vn, R1, R2, and I'm measuring the voltage across R2. So R1 and R2, they are in series with series in the voltage. So this is the voltage division. So your V out, which is the voltage across R2, V out is basically equal to Vn times R2 over R1 plus R2. Okay. Now, here is the point. Now, when I start moving this, rotating this, actually I'm going up and down. So your R2 value is changing. Your R2 value is basically changing. Now, when you change, R1 is not changing. R1 is basically the resistance between 1 and 3. So this is fixed, doesn't change. But R2 is between 2 and 3. So this, as you go up or down, you are changing R2. If you change R2, you are changing V out. And this is basically used for many applications. One of them is to control the volume. When you have a device, especially in the old era, now everything is digital now, but before we have everything analog. So basically in your radio, when you turn, or your TV, you turn on, I'm not sure if you have seen, now everything is remote control, everything with buttons. But if you have seen something that when you turn a knob to the right or to the left, the volume goes up or down, basically it's a voltage divider or a potentiometer. So basically you can increase the voltage. The voltage basically is changed to sound. And there is a sensor to do that. That will change the voltage into sound. This is what you hear from the speaker of your radio or cassette or TV, etc. Okay, I am quite sure I'm talking about some award that you guys never saw, maybe, or maybe you have seen it in old movies in the 90s. Okay, but I know that doesn't exist now. Maybe it's only in museums or so. But the potentiometer is one of the applications we use them is to control the volume of all devices, and it has many other applications. Okay, now let's talk about the I think you might have an experiment using this potentiometer, but this is the most important thing, and want you to pay very good attention. If you are paying for, I mean, with me 90% attention, now I want you to pay 100%. Why? Because the coming experiments, you need to understand this circuit very well. And students, sometimes they have trouble with it, but if you understand what I will talk about here in the coming, I know how much time I have. Okay, around I have 25 minutes. I want to explain this one in details. Then you should have no problem with your experiment. This is a special circuit called the Wattston Bridge. So it's basically a bridge that has two legs. The first leg is R1 and R2. The second leg is R3 and R4. And it has a voltage. It's connected here. And here you measure a V out between point C and point D. This Wattston Bridge is used a lot in its instrumentation, and you will have an experiment using this. Now let's understand this. The Wattston Bridge works in two modes. The first mode we called the balanced mode. And we need to understand what do we mean by the balance mode. In the balance mode, basically your V out here, the voltage between C and D will equal to 0. So this is a reverse problem. We want to see what are the values of R1, R2, R3, and R4 that will lead to the fact that your V out is equal to 0. Okay, so we will derive this assuming that V out is equal to 0. Then we will see what are the conditions that if we have or if we met, then your V out will be equal to 0. So let's take KVL around, this is your V out plus minus. So let's take KVL around this loop. Now we have two currents, I1 and I2. Obviously, I1 is going here. This is an open circuit. So I1 is going this way, and I2 is going that way. So with the current going this way, so it becomes plus minus, this way plus minus. So here you can say I1 R1 plus V out minus I2 R3 equal to 0. Now we assume V out equal to 0, so this becomes equal to 0, or we can say I1 R1 equal to I2 R3. So this is the first equation. Let's take KVL around this loop. Now I1 will be moving this way, I2 will be moving this way. So again, we'll do the same thing, KVL. So I1 R2 minus I2 R4 minus V out equal to 0. Again, V out is equal to 0. So I1 R2 equal to I2 R4. And this is equation 1. Let's divide 1 with 2. So divide equation 1 with equation 2. So you'll have I1 R1 divided by I1 R2 is equal to I2 R3 divided by I2 R4. So this will cancel, this would cancel, and this will give me this condition that if I have, then your V out equal to 0. So if R1 over R2 equal to R3 over R4, then your bridge is balanced and your V out is equal to 0. Now, in your experiments, you will work on this. So if I connect here between these 2 points, let's say an LED, a light emitting diode, like a bulb, if I connect here between these 2. Now, since V out is equal to 0, the current here will equal to 0. So your light bulb will not work because there is no current. Once you start to change the values of R1, R2, so this conditions is not valid anymore, then your V out will not be equal to 0, and there will be a current going there. So if the bridge is balanced, okay, then there is no current here. And if you connect any load here, yes, we divide equation 1 by equation 2. Yes, this is what I did. I divide this equation by that equation. So if your bridge is balanced, then there is no current. And if I connect anything here, then you will have, it will not be working. So this is the Wattston Bridge under a balanced condition. Let's have this example. So here what I did when I take the, when I just divide this over this. So I1 will cancel and I2 will cancel because in this term we have I2, here we have also I2, so this will be canceling. So we'll have R1 over R2 equal to R3 divided by R4. Hopefully this is clear. Hopefully everyone can see this. Okay, now let's see this example. Here we have R is given to us as 750 ohm. Okay, and R1 is equal to 15 kilo. R2 is equal to 25 kilo. R3 is equal to 5 kilo. R4 is equal to 3 kilo, and R5 is equal to 5 kilo. So these are the resistors we have here. It says here find the power absorbed by the 3 kilo ohm resistance. So by R4. So how much current goes here? We have the resistance, so the power is I squared times R. Now, when you have a question in bridge format, the first thing you have to do, you need to check, is your bridge balanced or not balanced? So this is the first thing you need to check. Okay, so check if the bridge is balanced. So we need to check that. So let's say how we do that, divide R. Now, it has to be this resistance over this. This is called the first leg. This is the second leg, which they are connected with the voltage supply. Okay, so we will check, is R1 over R4 equal to R2? I will address your questions now. Just let me finish. Equal to R5. Is this correct or not? Okay, R1 is 15 divided by 3. Is it equal to R2 25 divided by 5? Indeed, yes. So if this is the case, if these two are, or this condition is met, so VA will equal to VB, or VAB equal to 0, which will lead that your IAB will equal to 0. So there will be no current here. There will be a current in R1 and R4 and R2 and R5, although I connect here a resistance. It's not an open circuit anymore, but there will be no current. Why is that? Because VA and VB are the same. So when there is no potential difference between 2 points, there is no force to move the current between point A and point B, because the voltage here is equal to the voltage there. There's no pressure difference, if you may say. So the current cannot flow here. Then, yes, here R1 over R4, this is R4, and this is R2 divided by R5. So IAB equal to 0. If IIB equal to 0, then I can take this out to make the circuit look nicer for me. So I will have here my R. This is my R1, R4, R2, R5. So if this is my current I, then this current will be I1 and this current will be I2. So we will do something similar to what we did in the previous example. First, I will find the equivalent resistance, find I, then this current I will be using current division to find the current in I1 or I2. Now, the power absorbed by R4 is the current that goes here, I squared times R. Okay? So let's find the equivalent resistance. So these two are in series, these two are in series, and everything here, this branch and this branch is in parallel. So let's find R equivalent. So we have R1 plus R4, R1 plus R4. This one becomes 15 plus 3 equal to 18 kilo ohm. And we have R2 plus R5, they are in series. So this is equal to 25 plus 5, which is 30 kilo ohm. Okay. And now these two are in parallel. So we will have R1 plus R4 is indeed in parallel with R2 plus R5. So this is equal to 18 times 30 divided by 18 plus 30. And this will give me 11.25 kilo ohm. Now, so all of this, I can just rewrite it here, redraw it here. We have the R and this parallel. So we will have here your one resistance 11.25 kilo ohm. So what is the total R? Your total R equivalent will equal to the 0.75 kilo ohm, which is 750 ohm, 0.75 kilo ohm plus 11.25 kilo ohm, which give me 12 kilo ohm. So this is the total resistance of this. From this, I can find I. This is very similar to the previous question, but the configuration is still a bit different. So your I is equal to 192 divided by 12 kilo, and this gives me 16 milliamp. Okay, so I have here 16 milliamp entering this circuit. It will see two branches. So I need to find I1. Yes, the total voltage is 192. This voltage is 192 volt. So your I1 is equal to I, the main current, times this, the other the R2 plus R5, R2 plus the R5 divided by this leg and this leg. So the R2 plus the R5 plus the R1 plus R4. And we have everything here. We have R2 plus R5 is equal to 30 kilo amp. R1 plus R4 is the 18 kilo amps. And your I, 16 milliamps. So if you just substitute, this becomes equal to 10 milliamp. So I know the current that goes here. So the power absorbed here, the power absorbed in this resistance, your P is equal to I1 squared times R4. Just substitute 10 milliamp square times R4 3 kilo ohm. So this gives me 0.3 watt. Okay, so this is the power absorbed by this resistance. So again, first you check is whenever you see a Wattston Bridge question, you need to check is it balanced or unbalanced. If it is balanced, how you do that? You check the leg, the two resistance, R1 over R4. Now, don't be fooled by this is R1 and R2. Don't be fooled by the symbols. It's not, it is, this is one leg, this is the other leg. So you divide the ratio of the two resistors in the same leg. So here it is called R1 and R4. So it doesn't matter what I call it. I call it RA, RB, RC, RD. I call it anything. So R1 over R4, is it equal R2 over R5? If it is yes, then there is no current here. The VAB is equal to 0. Then this branch can be taken out and the circuit become much easier to analyze. Now the question is, what if it is not? If it is not balanced? Which is the second case. So what if R1 over R2 is not equal to R3 over R4, the question is, what will be my V out? And this is an extremely important formula. We will be using it a lot when we take the second or the coming class when we talk about the strain gauges, because the strain gauges actually, we put them in a Wheatstone bridge. Okay, so we need now to find what is my V out. Okay. Now here again, I1 and I2 plus minus plus minus. This for you don't need to know how to derive the formula, by the way. You don't need to memorize the formula because the exam is an open book exam, but it's good to understand how we derived it. Okay. And this is so it's the same, everything exactly the same, except here your V out is not equal to 0. That's the only difference. So let's write down the equation that we derived last time. V out is equal to I2 R3 minus I1 R1. Just KVL here. This is the same. We said last time this is equal to 0. Then I2 R3 is equal to I1 R1. This is the only difference. Okay. Now, so this is now is not equal to 0. Now, let me take KVL in these two outer loops. Okay, so let me take in this loop and in the outer one. So let's start with this. So I1 R1 plus I1 R2 minus Vs is equal to 0, or I1 R1 plus R2 equal to Vs. This is one equation. Then I will take KVL in this loop, outer loop. So I2 R3 plus I2 R4 minus Vs equal to 0. Take I2 as a common factor, comes R3 plus R4 is equal to Vs. So from 1, this is 2, from 1, I1 is equal to Vs divided by R1 plus R2. And from 2, I2 equal to Vs divided by R3 plus R4. So I have now a formula for I1 and I2. I will take this and substitute it here. So from this, your V out is equal to I2 times R3, which is Vs divided by R3 plus R4. This is just I2 times R3 minus I1, which is this, Vs over R1 plus R2, okay, times R1. So now we just need to add these two terms together. Okay, so we need to multiply R3 plus R4 times R1 plus R2, okay, to unify the denominator, and then do the addition of this. So this is everything I have here. Okay, so your V out will equal to your Vs. So what we'll do here, I'll just take Vs as a common factor from this formula. This is the only thing I'm going to do now. So Vs become, open a bracket. So this is R3 over R3 plus R4 minus R1 over R1 plus R2. That's it. Okay. Then just let me add these two terms together. Okay, I will go back. What's your question here? Someone asked me to go back at the slide. You have a question? Daniel? Oh, okay. No need to copy. The slide is there, so you don't need to copy. Maybe it's better, you guys, if you wanna write with me, just print this and have it in front of you, so that you don't need to worry much about copying. You need just to worry to understand what I'm talking about here. Okay, so here this becomes equal to Vs multiply R3 plus R4 times R1 plus R2. This divided by this times this, so this becomes R3 times R1 plus R2 minus, same thing here, this becomes R1 times this divided by this, so this will cancel, so it becomes here R3 plus R4. Okay, let's open the brackets. So Vs times R1 R3 plus R2 R3 minus R1 R3 minus R1 R4 divided by R3 plus R4 times R1 plus R2. Now this will cancel with this. So your V out, and this is your formula that you will be using a lot in this course, R2 R3 minus R1 R4 divided by R3 plus R4 and R1 plus R2. So if the R1 over R2 is not equal to R3 over R4, then this is the formula. Let's see. What if it is equal? What if R1 over R2 equal to R3 over R4? It means that R2 R3, R2 times R3 is equal to R1 R4, or R2 R3 minus R1 R4 is equal to 0. And this becomes equal to 0. So this is the general formula. So if R1 over R2 equal to R3 over R4, then this whole term becomes equal to 0, and this is the balance condition. If it is not, then this is not equal to, this will not be equal to 0. And if you are interested to find the voltage between points C and D, and your system or your bridge is not balanced, this is the formula that you need to do. Okay, so this is very important to understand, so that you will be able to understand your coming experiment, where I think you will use a photoresistor, where a photoresistor is a resistance that its value uh, will be changing with light. Okay, how you can use this formula? This formula, we will be using it a lot starting from Thursday lecture, in the lecture, because we will be using a Wattston Bridge in balanced and unbalanced condition to measure the resistance of the strain gauges, and we'll talk about that in Thursday. So I will post the new set of notes tonight, so that this is become for Thursday and maybe for next Monday. Let me see if you have any question here, guys, before we conclude. How to use this formula? We will learn about that on Thursday. So that V out equal to Vs in value. No, V out is equal to Vs times this resistor. Depends what are the values of the resistors. Okay, so but this you just substitute the values. It's plug and play. That's it. Okay, so V out would be Vs times those values of the resistance. Let me stop the recording.